CMOS, which is sitting at the bottom. Just okay, and then we have a kind of a static load resistance. Okay, this is the source, this is the gate, and this is the drain of this amplifier. Okay, yeah, this is where exactly we take the output. Okay, this is what we really have now, and this I call it as something like an NMOS. So here you can see that source is connected to ground. Okay, the source is basically connected to what is happening to this now. This. Okay, that is ground basically. Now, if you see, there is a resistance on top of this NMOS. Okay, so, and this is what I mean by the resistance. And designing parasitic resistance, okay, is one of the disadvantages that we have in CMOS. Okay, so your NMOS is an active device, whereas resistance is the parasitic. Okay, so and then in order to design this resistance on an IC, okay, it's not feasible because this resistor occupies more area of the space. Okay, that's one thing, and then this particular resistance dissipates more power. Okay, so that is heat dissipation basically. So typically the static resistance or the resistor, the passive device that we are connecting as a load resistance, okay, at the drain terminal, is basically occupies more area, the passive, and it dissipates more heat. Okay, so in order to overcome this, we try to use something called the diode connected MOSFET. Okay, so instead of this load resistance, we'll try to use a MOSFET which will be acting as a resistance now. Okay, so we'll see what exactly this means. Okay, so now we'll try to replace the resistance which is sitting on top of NMOS with the active device. Okay, so this is the equivalent I'll write in terms of the active device. Okay, again we have an NMOS which is sitting at the bottom. There won't be any change. Source is grounded. So now either I can use a PMOS. Okay, either I can use a PMOS. This is my drain, the source, the gate connected to the drain. Okay, so this is this, yeah. Okay, this is my source, this is my gate, and this is drain now. Okay, so gate is shorted to the drain. In other words, now it becomes a two terminal, right? So the source terminal and the drain terminal, and this is what we'll try to do this now. Okay, so we'll try to okay, so this gate is now connected to this. This is my VDD. Okay. This is what my Vout is all about. So now, whatever the transistor I have and top of the NMOS, okay, this is what. This now exactly, it's a two terminal now because gate and drain are shorted now. Okay, So I have one source that is connected to VDD and the drain that is connected to VO. That is nothing but what drain connected to the drain of NMOS. Okay. So now this is the dynamic load that we will try to see. Okay. So here, suppose if I say the RD that we have used in the figure 1 is kind of 1 kilo ohm RD. Okay. Just a minute, I'll just close this and open the new one. Am I audible now?
Yes, sir.
Some issue. So I could restart my system. Yeah, so I'll just go through this. So the common source amplifier. Okay, so this is what we're going to discuss in terms of this, and then as I said, so we use an NMOS. Okay, so which has source, the gate, the drain, and source being the connected to the ground. That's why we call it as a common, or source is common point between the gate and the drain. That's what it is also. And then we'll try to have this load resistance. Okay, so which we call VDD, and this is where we take out our V out, and this is what as V in is all of. Yeah, this is what. But as I said before, so even if you have the parasitic, I mean the passive device, not the parasitic, it's a passive device resistance. So in an IC, so realizing this passive device resistance or the capacitors, okay, occupies more space and more area. That's one disadvantage. Okay. The second disadvantage or the drawback of using this passive devices, it dissipates heat. Okay. So that's why we have to ensure that we have to use some dynamic resistance or an active resistance, okay, in order to overcome the occupancy of more area and also this heat of the dissipation problem. Okay, so for that we'll try to use either the PMOS, that is the diode connected MOSFET. Okay, so that is where the gate and the drain are shorted. Either I can use a PMOS or I can use an NMOS. For example, if I go with the PMOS, this is the source, the drain, the gate we have, and the 4 terminal that is connected to the source. Okay, that is VDD. We are not dealing with that. So now what I try to do is I try to connect or short the gate and the drain. Okay, so now it becomes a 2 terminal now. Yes, I have one source terminal and the drain terminal. So that's why it is called as kind of a diode. 2 electrodes, right? So 3 terminal now is converted to a 2 terminal. Now, suppose if RD is some 100 ohm, there will be some potential drop or voltage drop across this, and there will be some current flowing. Yes. If R is fixed to 100 ohm, what is the current flowing here? Will it vary or it will be fixed? Or it is a constant current that will be flowing through this RD? Fast. Yeah. And given the R value there 100 ohm, no doubt there will be a drop across that resistance and there will be current flowing through that, right? So the current flowing through this RD from VDD, will it be a constant? Will it be varying or what exactly? Fast.
Constant.
Ah, fast. It's a varying component, the current, or it is a fixed component, constant, or what? Fast. I want you people to respond fast. Yeah, if VDD is fixed, RD is fixed, what is the current flowing through that?
Constant, sir.
It's constant, right? Okay, now this passive device RD okay, which allows the constant current to flow, okay. But I have to ensure that the active device now, which I'm using in place of this RD, that means I'll just show how exactly I can go ahead with this. This is my NMOS, okay, with the gate, the source, the drain, and this is connected to this. And now I have a PMOS, which is now sitting at top, okay, the source, the drain, and now it is not acting as kind of an active device, even though it is an active device, but it is now has to play a part of resistance, okay. And now can anyone tell me when exactly I can replace this PMOS transistor now, which is a kind of diode, in place of the RD now? Under what condition of this transistor? Yes, or how I can, or when I can say this and this RD and this PMOS transistor where gate is connected to the drain or the shorted is equivalent, when I can say?
When it passes constant current, sir.
Okay, exactly. That's why I asked you. I told about when VDD is fixed and R is fixed, what is the current that is flowing through RD? Yes. Now, when I can make this PMOS transistor, which is now acting as a diode, to be giving the constant current, under
Forward bias.
under what region of operation this transistor should be in order to pass or allow the constant current through it? Yes. All this green has been already thought. When this transistor, the PMOS, that is sitting on top of this NMOS, where gate is shorted to the drain, will ensure a constant current flowing through that. Yes? Anyone? Under what?
So saturation.
Exactly, it has to be a saturation. Okay, the moment I make this particular transistor operating in saturation, and we know that the IV characteristics, right? The output characteristics, yes, the moment the transistor is being operated in the saturation region, its current is constant. Okay, so that's why ensure that the PMOS, which is sitting on top of NMOS, this is my NMOS. Okay, try to make this to operate in saturation region. So now, what should be the condition in order for this PMOS to be operating in saturation? Yes. What is the condition for that transistor PMOS to be acting in saturation? Fast. When it will be in saturation region? Yeah.
So VGS should be less than VTP.
VGS should be less than VTP. Okay, that means it should be on, right? On.
Yeah, then
Okay.
Vin should be less than VTP plus VDD.
V in. That means any of your gate to source should be less than VTP. That means assuming that this is on now. I assume that PMOS is on. That is this condition. But what is the condition for the transistor to be operating in saturation?
VDS less than VGS minus VTP.
VDS
Less than VGS minus VTP.
VGS minus VTP. This is what this is. I think this I go with the magnitude. Okay, so this is what we had seen, right? For an NMOS, VDS greater than VGS minus VTN. For a PMOS, VGS should be less than that. Okay, so I should ensure that the drain to source voltage, okay, the drain to source voltage should be less than the VGS minus magnitude of VTP. Okay, only when this condition is proved, okay, I can say that the PMOS, which is sitting on top of NMOS now, is acting in a saturation and there is a constant current flow. So most of the time, whenever you see the load replaced by these active devices, means they act as a load resistance with a constant current. Okay, now I can say this is a constant current source. Okay, now this is a constant current source because it is operating in the saturation. Okay, since it is operating in the saturation, provided this condition. Okay, now I can say that the PMOS and this resistance, now they are equal. Oh, this is fine. Why the passive component is replaced by an active component as a resistance? So now this particular PMOS is now acting as a resistance which allows a constant current to flow. In other words, this is acting as a constant current source now, which is equivalent to that RD. Hope this is fine with everyone. Yes, no? Fast?
Yes, sir.
Yes, right. Now, so I call this the bottom one as M1 and the top transistor as M2 now. Okay. And M2 is basically a constant current source for me. And M1 is nothing but what? My common source amplification is all about. Okay. So this is the NMOS transistor I use for common source amplification. Okay. Now again, it's an NMOS. Okay. What is the gain of this particular NMOS transistor? What is the expression? What is the gain that is given by? What is the gain of this NMOS transistor in this particular when source is grounded? We already studied. Anyone remembers what is the gain expression given? Which is basically V out by V in. Okay. Anyone remembers? It is GM times S. Fast. Anyone remembers? Gain of common source. Okay. GM times RD. I mean, whatever that RD I have taken there. And it is minus. So this is what the gain. Instead of RD, I can simply write kind of R0. Okay. Instead of RD, it may be an R0. What is this GM is all about? What is this GM? What is GM? Yeah? Anubhav? Anubhav?
Yes, sir.
What is GM? Why this is there is a negative sign here?
So,
Yes, Monisha? Monisha. Okay, so she is absent for today's class. Anusha? She is also absent. Geeta Patel?
Sir, transconductance.
This is transconductance. So when you are knowing conductance, what is this negative is all about? What is minus negative sign there? What
sir,
it
output is
indicates?
inverted of input.
Output is?
Inverted of input. Nice.
Why output is inverted?
Sir, common source is same like common emitter configuration, where 180-degree phase shift will be there.
Okay, so this is because of 180-degree phase shift. Okay. Later I will ask you why this 180-degree, and this R0 is something like a load resistance now. Okay. This is the expression for gain. Can anyone derive this gain expression for me? This is typically for M1 transistor. This is typically for the M1 transistor, okay? Because that top PMOS is just a resistance for me. That's it, fixed resistance with a constant current supply. Can anyone derive how exactly to get this AV, which is V out by Vn, which is equal to minus Gm times the R naught of the RD? And how we get this? Yes, and anyhow, just see, if I just go with this NMOS, that is M1, so I'll just go with the next one, okay? Oh. Yeah. So this is my NMOS, which I call it as M1, okay? This is V in, this is grounded, the source, the gate, the drain, okay? This is where my V out is all about, and this is what my resistance R naught or RD, okay? Now I'm just EM and replacing the active with the passive just for our understanding, okay? This is what. And now we know that source is at ground potential, gate is where we are applying the input. So we have the gate terminal, we have this source terminal, yes, and between gate and this I'll apply. This is what my Vin is all about. My source is grounded here, yes. This is gate voltage. And is there any current flowing between the gate and the source? Fast? Fast?
No, sir.
No, because Ig is 0. Okay, so Ig is basically 0. So it is an open circuit here. Okay, it is an open circuit. That's why you call it as VGS, plus or minus. And then there is a drain to source connected because there is a current exists, right? And that current we give in terms of this source, okay? And then there is one resistance that is connected, okay? Just a minute. Let's rub this. Okay. Yeah, so this resistance, since there is only one resistance, I will take. And since the amplification when we are seeing, okay, it is all with respect to small signal model, okay? It's a small signal analysis, okay? In the small signal analysis means it is a variation that is happening. But this is my RD, and the RD1 is connected to the drain. This is where my V out is all about. And another terminal of RD is connected to what terminal or what thing? Yes? You can see one terminal is connected to V out, and that's what I have done here. And the other terminal of this resistance is connected to VDD. But since it is a small signal analysis, when I say VDD is a constant, there is no variation, it's a constant. So that's why my RD, other terminal, instead of VDD, it is connected to the ground. Okay, and Vin is the AC signal that we are providing. Is this clear? Oh, this is fine with the equivalent circuit? Yeah? This is the equivalent circuit of the above one. Yes? Fast. And why the direction of this current source is from drain to source? Yeah? Why it is something like this? This is what is I is all about. Yeah? Why it is so? From drain to source? Why can't it be in the opposite direction? Fast. Why the direction of current is from drain to source? Who will tell me? Fast. Hmm? Hmm.
Sir, because charges is supplied from source to drain.
Yeah, this is NMOS transistor. Okay, the electrons are moved from source to drain, so your current should be in the opposite direction, that is from drain to source. Okay, this is what is all about. Yes, that's why it is from drain to source. Now, so this is V out. Okay, so now if I want to have the V out expression now, okay, this particular current, so it is given by in terms of GM into VGS. Okay, so this is the voltage, open source voltage that is appearing at between the gate to source, that is seen at drain to source. Okay, it is the VGS into GM. Okay, I is equal to V into R, but this current, whatever this current is there, I, it is V times the R, but it is not the R, it is the transconductance, we say. And why the transconductance? We have already seen before. This is because of ID, the VGS. Okay, and it is typically a kind of IV characteristics of diode, right? Okay, if I just take 3 points, okay, that's what it is, linear, right? Yeah, if I just check with respect to this, okay, and we know that ID is the output current. Oh, this is output current. VGS is the input voltage. Yes. If I just have this at this point, there will be 180-degree phase shift. You can see that input is this, my output is the drain current, which is varying in terms of this. A small variation in input is giving me the large variation in the output. Okay, so since output is current and input is this, so that's why it is GM. Okay, and that's why this current is the VGS times the GM is all about. Okay, so that's why this current source is given by GM VGS, then it is RD, and current is flowing from drain to source, and the gate to source current, that is IG, will be 0 because of I input impedance. Okay, and this is what. Now if I want to calculate the V out, or if I want to calculate this node analysis, if I want to make, okay, so I can simply get something like minus GM time VGS. Okay, so this is what my drain current is all about. Yeah, into RD. So this is the I current flowing into the RD is nothing but what? V out. Yes, and what is VGS now? That is the input is there. VGS is basically VG minus VS. VG is basically Vin. VS is basically 0, that is grounded. So I can say that V out equals minus GM times Vin into RD, or V out by Vin is equal to minus GM times RD, and V out by Vin is nothing but what? Gain form. Okay, this is what I think this is. I had already explained this particular equivalent circuit in the earlier class sometime. Okay, but this is the equivalent now, and that is how I am getting the gain expression for this common source amplifier as minus GM times the RD. RD is the load resistance. Oh, this is fine. Why GM? Why it is not R we will be taking? Because output is the current, input is the voltage. So output by input is nothing but what we are getting, yes, with respect to this IV characteristics. Okay, input we are giving is the voltage, output is the current that we are checking with. Yes, So it output is ID by VGS. Okay, so R is V by I, whereas I by V will be my GM. So that's why. So here constant current source is given by GM times the VGS. And VGS is predominantly is nothing but what Vin, because source is at ground potential. If I substitute all those things, I get my gain AV, which is V out by Vin is equal to minus GM RD. Okay, this is not necessary for us to derive, but just explaining what is this all about. Okay, so this is from this we have to start in designing this common source amplifier. Okay, and that's what we'll try to do now. Okay. Yes, that's what we'll try to do. Okay. And just write that common source amplifier once again. Now we won't be having that. This is my M2. This is VDD. Source, gate, drain. This is shorted. Grounded. Source, gate, drain. V in, M1. This is my V out. Okay, this is what I have. And we just derived that AV is equal to minus GM times RD. Okay, but now RD is replaced by now this M2 transistor. So they have proven that RD, okay, is approximately equal to 1 by GM. Okay, RD is approximately equal to 1 by GM. Since it is RD corresponds to M2, I call this as something like M2, and this I call it as something like GM1. Okay, so the gain of the NMOS, I mean this common source amplifier, okay, is GM1 RD, because this gain is corresponding to this M1 transistor, and RD is replaced by this M2 transistor, and RD is approximately equal to 1 over the transconductance of M2. Okay, this is what. So now I have AV is equal to minus GM1 by GM2. Hope this is fine. Yes, we all came to know AV is equal to minus GM times RD, and here I have two transistor M1, M2, and gain is with respect to M1, so that is AV equal to minus GM1 times RD, and RD corresponds to the R2 transistor, M2 transistor, so RD is approximately equal to 1 over GM2. Okay, so in other words, AV is now minus GM1 by GM2, and this gain, okay, of this transistor is theoretically calculated. We are not going to calculate, we are directly going to substitute that. Okay, it is given by 2 times mu n, be very careful, GM1 with respect to my NMOS, GM2 is with respect to my PMOS. So the numerator is with respect to GM1, it is 2 times mu n COX W by L1 into ID1. So where all you are seeing the subscript 1, it corresponds to NMOS. All divided by, for GM2, the same, 2 times, instead of mu n it is mu p, COX W by L of this PMOS, and it is ID2. Okay, so the equivalent terms, if I cancel, it will be left with mu n. What all it will be left with? Yes, mu n by mu p, W by L1, this is square root of mu p into W by L into 2. What happens is, what about ID1 and ID2? Yeah, what about ID1 and ID2? Are they equal, same, or different? That means the current that is flowing through this is ID2, and it is constant, and the same current has to flow in this also. Yes or no? Fast.
Yes, sir.
Yes, so that's why the current flowing through the M2, that is the load resistance, has to flow through the active device. So that's why ID1 equals ID2. So this is, and PMOS is acting in the saturation, should act in the saturation region, so that my ID2, that is the current flowing through, is constant. And tell me in what region my NMOS should be operating for an amplifier, for the amplification. Active, it has to be in the active region, okay? It has to be in the active region. Make sure. So a M2 PMOS, which is acting as a load, should act in saturation region. We should provide all these necessary conditions, and the NMOS, okay, it has to be in the active region in order for amplification. Okay, so this is where we are, and we know that mu n is approximately equal to twice the mu p. Okay, it varies between 2 to 3. Okay, you can assume 2.5 mu p or 3 or 2. Okay, I'm just assuming this. If that is the case, it will be what? Minus root of twice mu p by mu p, w by L of 1 divided by w by L of 2. This mu p gets cancelled. So what is there now? AV equals minus times square root twice w by L of 1 divided by w by L of 2. Yes, this is what. Yes, now there are variables now. We don't know AV, and I should find out what is my W by L and W by L of 2. Okay. So this is what. So now what I will try to assume is, since it is an amplifier and it is a gain, okay, so typically it will be greater than 1. I just let AV is equal to something 10. Okay. So if I substitute in the above expression, so it is 10 equals minus. So what I'll try to do is, I'll take the square root this side. It is 10 square minus twice W by L by 1 divided by W by L of 2. Okay. In other words, I'll just write this up. It is 50 equals W by L of 1 divided by W by L of 2. Okay. So I can assume the NMOS transistor width and the length ratio. Okay. Correspondingly, I can get the width and length ratio of my PMOS. Okay. So assuming W by L of NMOS is something like 10 by 2. Okay. I can easily calculate what is my width to length ratio of 2. Okay. This is how you'll try to calculate. Okay. Assume gain, you can assume 10 or 20 or 30, and then the width and the length, and make sure that your width is greater compared to your length. Is that clear? Yes. Don't have your length bigger and the width smaller. Okay. It is the length that is very smaller, because we are all dealing with the short channel transistors. Okay. Or the scale transistors. Hope this is fine. What is W by L of PMOS I will get now? If this is the case. Yeah. W by L of this is 1 of W by L of 2. This is 10 by 100. What I get now? 1 by 10. Something like this. Okay. You can just feed this information. Okay. So, but you should know the gain of the amplifier. Then the RD is approximately equal to 1 by GM2. That is the transconductance of transistor 2. And finally, AV is equal to minus GM1 by GM2. Okay. And then substituting the value of GM1 and GM2, I get something as AV equals to this. Okay. Then, since it is a common source amplifier, there is an amplifier happening. I can assume the gain value to be more than 1. Typically, I can assume 10, 20, or 30. Okay. Assuming that, then you assume your W by L of NMOS transistor, Okay, 20 by 2 or 10 by 2. Then correspondingly you will get what is the width to length ratio of PMOS. Okay, so you should know the W by L of NMOS transistor. Okay, the W by L ratio of PMOS transistor. And in order to get this, you assume your gain to be some 20, 10 or 30, that is greater than 1. Okay, then you can choose either this or this. Better you choose the NMOS transistor, you will get what is your PMOS transistor W by L. Okay, so in your electric circuit, okay, you should take one NMOS that is already given over here, okay, and then the PMOS, and you draw accordingly the circuit. Then in the parameters, the M2 transistors, okay, you have to ensure that width and length that you calculated and got, and similarly you have to put the values of WL of this M1 transistor. Okay, after having this schematic, then we will be going for 3 analysis. One is, first we have to go with the DC analysis, then we will go with the transient analysis, and then finally we go with the AC analysis. And why this DC analysis we were doing for this inverter circuit is very much visible over here. Okay, this is what the design of common source amplifier is all about. The gain. Okay, so finally the moment I do the simulation, okay, applying some input, I should get finally the gain to be somewhere near 10. Okay, this is the theoretical value that I have assumed and put. Once I do the transient analysis and all, I should get the gain to be somewhere around 10, approximately maybe 12 or 13, nearby that. Okay, if something variation is there, more variation, I can play with respect to this mu n is equal to 2 mu p. If you have substituted 2 and if you are getting gain as somewhere 15, make this 2.5 and correspondingly calculate what is your W by L of NMOS and PMOS. Check the again, change all the parameters and check. Okay, you can play between 2 to 3 mu p of mu n. Okay, choose which is the best relation between mu n and mu p, and correspondingly that gain is very near to the theoretical that we have assumed. Hope this is fine. Any clarification in this design of common source amplifier? Choosing the W by L of M1, choosing the W by L of M2. That is where it is important. And how to get that expression, it is proven, and how to get this W by L also is done. Yes, any clarification in this common source amplifier design? Fast.
Sir, excuse me, sir.
Yeah.
Sir, should we neglect that negative symbol, sir, in that last expression?
What is the point in using the negative there? It is always there, man. It is always there. But see, that is output with respect to input. Is that clear? If I am giving input to be somewhere like this, yes, if this is my input, what will be my output? Output will be the 180-degree phase shift. There is a phase shift. Here the positive becomes the negative here, positive becomes negative here, negative becomes positive, but with the amplified version. Oh, this is fine.
Okay, sir.
Yeah, that width and W, the W and L cannot be a negative. Is that clear? So that's why finally I'm not using that minus sign over there. Okay. Yes.
Okay, sir.
Yeah, gain will be there, but with the negative sign, means that negative is basically 180-degree phase shift. Hope this is fine with everyone.
Okay, sir.
Yes. Yes. Any other clarification? Hope this is understood, that common source amplifier design. Why we are using a PMOS as a load on top? Why not we are using a passive device resistance itself? Okay, because of the area constraints. Because IC is very compact, right? The moment I am building a passive component there, it becomes very trade-off with respect to area. It consumes more area, and since it dissipates the heat, so it's better to use the active device, and that is what we have made. Okay, so transistor we are making it to act as a diode. Okay, and acting in a saturation region, ensuring that there is a constant current source. Whereas the bottom NMOS, where we are applying the input, that is be acting in an active region. Okay. Why? Because we need the amplification. And even we derive the gain of the amplifier. This common source is minus times GM into RD. How we derive and what is GM is all about, right? That is ID by VGS. Yes, any clarification? Fast. Yes, no, fast. If no, I think we can stop here. I have a meeting to attend, so. Yes? Okay.